So in this video, we are going to talk about the addition rule, okay? And this rule is about probabilities that involve or statements. So that's really the key word there is the or. So the probability that A occurs or B occurs is given by the sum here, the probability of A plus the probability of B minus the probability that A and B both occur. Okay, so this is like the overlap. And one way to think about the addition rule is to think about those Venn diagrams we used to make. So let's suppose this represents my sample space, this rectangle. And let's suppose this represents event A and this represents event B. So the probability of A or B, that can be represented by shading everything that's in A and shading everything that is in B, and that is A or B. Okay, but the problem is if I just add together these two things, I've double counted the middle portion, and that's why we subtract it off. We subtract off probability A and B, so we don't double count. So let's look at an example here. 2 dice are rolled and the sum is calculated. So what is the probability of rolling an odd or a number less than 5? So here's the key here. I see the or statement. So what is the probability of rolling an odd? So rolling an odd or a number less than 5. So if I apply the addition rule, this would be written, so the probability of, let's say, an odd, so that's an odd sum, or a number less than 5. Let me just write it like that. And using the addition rule, this would just be the probability of rolling an odd sum plus the probability of rolling a number less than 5 minus the probability of rolling an odd sum that is also less than 5. So this is nice because it just breaks down the problem for me. So let's think, what is the probability of rolling an odd number? Let's focus there and just break things down. What is the probability if I roll 2 die and I add the sum, what is the probability to get an odd number? So remember that this is what our sample space S looks like if I roll 2 die. And notice how we have this alternating pattern. So 1 plus 1 is 2, so that's even. 1 plus 2 is 3, that's odd. And then we have 1 plus 3 is 4, that's even. And then we have odd, we have even, we have odd over here. And then going down here with this number, 2 plus 1 is odd, even, odd, even. So we just have this alternating pattern. And as you can guess, half of these numbers will give us an even sum and half will give us an odd sum. So the probability the sum is odd is going to be half, or 18 out of 36 of those sums. So what is the probability the sum is less than 5? So let's go back to our sample space, and so you can see this sum here is less than 5. I'm circling everything here where the sum is less than 5. So sum here is equal to 5, equal to 5. So sum is less than 5 here, and that's pretty much, sum is less than 5 here. So just in this corner, and you can see once I get out of the corner, the sum is equal to 5. So there's 1, 2, 3, 4, 5, 6. The sum is less than 5 in 6 out of 36 occurrences. Okay, so remember I've double counted though in terms of odd and sum less than 5. So let's look at the intersection here. So how often does it occur? What is the probability that I get a sum that is odd and less than 5? So all the less than 5s live over here, and how many of these are odd? Well, this one is, and it looks like these are all even. So we have 2 over 36. Because only when the sum is 3 do we have an odd sum. When the sum is 2 or 4, we have an even sum. So using the addition rule, we have 18 plus 6 minus 2, that's 22 over 36, which can be reduced to 11 over 18. And I'm going to leave that in fraction form. But you could convert that to a decimal and round. So 11/18, that is the probability of rolling 2 dice, and the sum is either odd or the sum is less than 5. So one of those two things happen or both occur. So let's do another example. In this example, a single card is drawn from a standard deck of 52 cards. What is the probability of drawing a red card or an 8? So again, I see the or statement. So what is the probability of drawing a red card or an 8? So let's just write that down using the addition rule, red or 8. So I'm just going to break the problem down for myself to make it easy. That's going to be the probability of red plus the probability of drawing an 8 minus the probability of both occurring. So I'm getting rid of that double counting. And let me remind you once again, a standard deck of 52 cards. We've got our red cards down here. They're called hearts. And we've got another bunch of red cards down here called diamonds. So there's 13 hearts and 13 diamonds. So we can say the probability of drawing a red card is going to be 26, so 13 plus 13 over 52 cards. And what is the probability of drawing an 8? Well, it looks like we've got 4 8s here, and that's it. So I've got 4 out of 52. And then the question is, how much did I double count? Well, when does it occur that a card is red and it's an 8? So that's the 8 of hearts and that's the 8 of diamonds. So we double counted 2 cards there. So that's 2 over 52. So now if I perform the math here, I get 28 over 52. And that reduces down to 7 over 13. So 7/13 is the probability of selecting a single card from a deck and getting either a red card or an 8. So that means either you got a red card or you got an 8 or you got a red card that is also an 8. So here's a new rule for you. It is called the complement rule. And so remember the complement of an event. Recall that if this represented my sample space and this represented my event A, then the complement of A is like everything that is not A. So it's the opposite of A, basically. And we can write that in different ways. Some people use this notation, some people use this notation, some people use this notation. The main rule that we have here is that if you want to calculate the probability of A complement, that is going to be equal to 1 minus the probability of A. So let's do an example so you can see how that works. So a single card is drawn from a standard deck of 52 cards. What is the probability it is a face card? So if you recall, the face cards are the jacks, the kings, and the queens. So here are my face cards over here. And so you can see there are 12 face cards. So the probability of drawing a face card is, 12 over 52. Okay. And then it says, what is the probability, what is the probability it is not a face card? So if the single card that we've drawn from the deck is not a face card. So probability not face card, or you could write A complement, or however you want to write this, is going to be using this rule. It's going to be 1 minus the probability of getting a face card. So that's 1 minus this number, 12 over 52. And that leaves us with 40 over 52. And that can be simplified down to 10/13, written as a fraction. But you could also write that as a decimal if you want and round it. The very last thing we're going to take a look at is the complement rule for at least one events. So when you see the phrase at least one, you can use this rule. And the rule basically states that the probability of at least one, whatever you're talking about, is equal to 1 minus the probability of none. So basically, at least 1 is the complement of none. And then that's why we can use the complement rule here. Okay, so a coin, so let's do an example. A coin is tossed 7 times. What is the probability of getting at least 1 head? So there is our key phrase there. What is the probability of getting at least 1 head? So I'm going to write this using the complement rule. The probability of at least 1 head is equal to 1 minus the probability of no heads. So what is an equivalent way of saying no heads? Well, that would be tail, 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 tail. That is the only way that you can get no heads. So that is the complement of this event. So we would say 1 minus whatever the probability of getting tails, tail, tail, all tails. Okay. And so what is the probability of getting all tails? So recall that in order to calculate a probability like this of equally likely of outcomes, we need to know the number of things in the event that we get tail, 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 tail. So let's just call that 7 tails. Minus the number of things in the sample space. So if I flip a coin 7 times, how many things are in that sample space? Well, remember we use the counting principle, and we would say, okay, let's think about each toss as a stage in the counting principle. And 1, 2, 3, 4, 5, 6, 7. And how many outcomes are possible in the first stage? Well, just heads or tails. I flip the coin again in the second stage. How many possibilities are there? 2. And we can proceed in this way. So this is just using a counting principle that the total number of possible outcomes when we flip a coin 7 times is 2 to the 7th, or 128. So this is equal to 1 minus something over 128. And how many outcomes are in this? Well, there's just 1, right? Just getting all tails. So my final answer is 127 over 128. You can enter it as a fraction like that, or you can write this as a decimal. So that's 9921875, which rounds to, if I round that to a percent, you can see that's about 99.2%. So that's pretty high. You have over a 99% chance of getting at least 1 head when you flip a coin 7 times. You can also think about this in terms of births in a really simplified sense. So if a family plans to have 7 children, and we assume there's a 50% probability of having a girl, what is the probability that out of 7 children you will have at least 1 girl? So it's over 99%. So that's just another way to think about it and put meaning in this.